This presentation is dealing with lithium versus lead-acid batteries and the benefits, for the most part, of lithium in emergency power applications. With the low voltages that we're usually dealing with, 12 to 28 volt, it's not easy to get electrocuted at those levels, but it is easy dealing with these high current batteries to burn yourself. So you have to be very careful with wrenching between posts and not melt your face off, plus all the sulfuric acid and lead acid batteries that could melt that thing down. It could blow up in your face. So if you don't know what you're doing, don't be cavalier about it. I recommend a hybrid setup usually for emergency power backup for residential applications, and that's because the batteries and solar systems for power emergency situations is so expensive, and but you don't really want to run your generator 24/7 a lot of times, and when the lights go out. So if you have a modest battery backup, then it can take over light duty loads for hours during the night, especially when you want it to be quiet. And one of those reasons is a generator has a minimum power that it's going to use. It's going to burn fuel even if it has no load on it. That's called the turn down ratio, like the U2000. Very efficient little generator, but it's going to burn fuel at a rate as if 400 watts was hooked to it, even though nothing was connected to it. On the other hand, an inverter that can output 2000 watts like our EU2000, but only draws 10 watts with no load applied, has a 200 to 1. Just so we're all on the same footing, we're going to start with some terminology and just get that out of the way. Amp hours is how we gauge the capacity or energy within a battery of the same voltage. So if you have a 12 volt 80 amp hour battery and a 12 volt 100 amp hour battery, you know the 100 amp battery has about 20% more energy or capacity in it. Amp hour is a combination of the amps drawn from a battery times the hours that amperage is drawn. So you multiply those two together and you get amp hours. So if you had 1 amp from a battery, theoretically, if that lasted for 100 hours, that'd be 100 amp hours. Or if we had 100 amps drawn from a battery for an hour, then that would still be 100 amp hours. Or 5 amps for 20 hours, that would be 100 amp hours. Now, in practice, that 1 amp would last longer than 100 hours, and the 100 amps wouldn't last an hour on the same battery. So the standard is to measure the amp hour rating at whatever current it has to draw that will drain it to dead in a 20-hour period. Watt hours is a way we measure capacity or energy within a battery of various voltages. So we multiply amp hours times the voltage of the battery to give us watt hours, and you compare various types of batteries, apples to apples, that way. So watt hours, amp hours times voltage. So if we had a 12 volt 100 amp hour battery, that's the same as a 1200 watt hour battery. You also may see kWh, which is thousands of watt hours. State of charge and depth of charge are two sides of the same coin. State of charge is how much is left, and depth of charge is how much was taken out. So a battery with 80% state of charge has a depth of charge of 20%. Resting voltage is a voltage that a battery has when it's not being charged and it's not being drained after it's been given some hours to settle down to whatever that voltage is. So the resting voltage of a lead acid battery that's charged all the way up is about 12.6 volts. And a lithium battery, the resting voltage of a full lithium is around the 13.4, and that will vary some with chemistries. So you may have seen this chart we see on the right over here, and we see that 100% state of charge for this chart is 12.6. So this is a chart geared towards the resting voltage of a lead acid battery. You couldn't use this on a lithium battery. Charge cycles is the number of times a battery can be discharged to a given level and recharged before it loses 10 to 30% of its capacity. So a battery in a solar system, for example, gets cycled once a day, usually in the late afternoon, evening. It goes down, and when the sun comes out, it gets charged back up. So a battery that had a 1,000 charge cycle rating would last about 3 years in a solar application. Cold cranking amps is a specification not found on dedicated deep cycle batteries. They're found on starter batteries, which are generally not made to be discharged more than 10%. Marine batteries are a hybrid, batteries that have both, so do not make a good solar application. So I'd stay away from anything that has a cold cranking amp specification. We've got a couple lithium batteries here. Battleborn, 100 amp hour. The 4,000 charge cycles that it's rated at would last you 11 years, and you can use twice as much of this battery in a given day than a regular lead acid because it can discharge to 100%, and it weighs half as much. The 10-year warranty is, way more than you'd ever see on a lead acid. The Bioenno battery is almost exactly the same price once you factor in that it can't do 100% depth of charge. It doesn't charge as fast as the Battleborn, but still it charges twice as fast as a lead acid battery, and it's well tested for AMI issues, so you won't interfere with your ham radios. If you want to make your own battery, you can do that. You can buy all these parts off eBay all day long. The prismatic cells here on the left are in pouches. They're kind of flexible, so they encase them in these hard plastic boxes that basically one cell per box at 3.2. You strap 4 of them together to give you a 12-volt category battery, but then you have to hook outside this. You have to wire a battery management system to it so it will shut off if you run one cell down close to zero. So it's a little more clumsy and a little more external wiring, but it would save on money. Also be aware that the lithium polymer batteries, like many of the car batteries and the batteries in your phone, they're the batteries that could catch on fire. If they're left discharged for long periods of time or they're physically abused, where the lithium iron phosphate batteries, the LiFePO, though the chemical design on that is inherently much safer and very difficult to if not impossible, to get that thing to burn. So I don't recommend buying anything but lithium iron phosphate batteries for your application, which you can get that either way off these do-it-yourself sort of cells. Or you could go with a salvaged electric car battery for your backup needs. You can buy these salvaged batteries online, and some companies specialize in this, like this setup on the right here is a racked up Nissan Leaf set. They guarantee about 70% of the battery capacity left, and they come in this middle picture, these individual plates that can have a positive and a negative, and you can actually, if I understand, flip every other one of these to convert this between a 24 and a 48 volt system, depending upon how you bust it together. And also just to compare the price of those used ones, and I adjusted this price based on a 30% depletion of its capability. But compared to that Battleborn battery that was $950, it works out to 89 cents a watt hour, where the others are about a third or so of that price. Okay, for some examples of lead acid batteries, on the keeping in the 100 amp hour range here, you've got the Duracell, kind of budget oriented, that could not find a charge cycle rating on this, so I had to kind of assume the worst. It's just in a few hundred. The Trojan batteries are all good quality, and you've got a 600 charge cycles at 50% depth of charge, which is a standard depth of charge rating for lead acid batteries. And then the Trojan T105, probably your most ubiquitous golf cart battery you'll come across. And the RE here is a tweaked for renewable energy. So this particular one is made for solar systems. So you can see this one is a 200 25 amp hour, but it's physically about the same size as the others because it's only 6 volt and runs about $170. So when you're talking lead acid batteries, they only recommend you drain it down to 50%, and less is better as far as getting more charge cycles out of it. So if you limit this to 50%, then a 100 amp hour battery is really only a 50 amp hour battery as far as practical use. Taking into account the lack of capacity in the lead acid battery, a 100 amp hour lithium battery is equivalent usability wise to a 200 amp hour lead acid battery. The cost is still $650 more for the lithium, but it saves you 86 pounds. Okay, let's take charge rate into account for our battery comparison here. So if we have the C is used in the battery world to represent the capacity of a battery in amp hours. And a bio-NO battery generally has a C/5 or a 20% charge capability. So if we have a 100 amp hour bio-NO battery, then we could charge that at 100 divided by 5 is 20 amps. A battle-born battery is C/2, so that's 100 divided by 2 is 50 amps. A lead acid battery has a C/10 or 10%, so we could charge the lead acid battery. Standard is around that C/10 at 100 amp hour would be 10 amps. A quick word on three-stage chargers in relation to lead acid batteries. The lead acid battery will allow you to do a bulk charge here at about 8% of the battery capacity up to that point in a constant current. So if you had that previous 100 amp hour battery, if we were charging it at 10 amps, then it's going to stay at 10 amps through about 80% of the recharge. And just a quick word, that 10 amps, you have to buy the right charger to get that 10. If you connect a 20 amp charger to this thing, it's going to charge at more than 10. It'll be close to the 20 amp point, which for that 100 amp hour battery would damage it. So we charge up to 80%, and the voltage at that point here represented in blue, the voltage would get up to a point where you don't want to exceed that, because then it crosses a threshold where the acid in the battery starts to percolate and burn off. So we don't want the drink to evaporate our acid, so we keep below that voltage. But as the voltage of the battery comes up, then the current in the red line naturally drops off down to a point where it's just like about 2 or 3% of its capability, and then it'll go ahead and trip off into a float mode, which it could stay in indefinitely. Okay, so how long would it take to get from 50% depth of charge, which we're allowed to routinely do with a lead acid, back to fully charged? I'm not going to go through all the math on this, but the bottom line is it will take about 10 hours to get through a full charge on a lead acid battery where we're draining it to 50%. And that really doesn't matter if it's 200 amp hour draining 100 amp hour or a 800 amp hour drain 400 amp hour. If it's draining at 50%, it will take about the same amount of time. Okay, so that 10 charging hours for that lead acid battery to cover from 50%, which is our standard discharge, and it doesn't matter how big or small the battery bank is, it's going to be about the same recovery time. So if you got 10 hours to recover, then you plot that over your output of your solar system here, and the maximum point of the solar system is usually set to where that's the point where we're charging our batteries at the optimum point, say that 10% point, which means the rest of the day we're charging it less than what we need. So to figure out what kind of total wattage we're getting out of this thing, we take the short lines and we kind of stack them up on top of the longer lines in the lump here, and we square it off, and what that comes out to for my location in Southern California as 5 sun hours in the wintertime. So you see there's a problem there. If I only have the equivalent of 5 hours of solar noon output out of my solar system, and I need 10 hours to recharge that battery, I'm not going to even get close to being fully charged for that battery. You can see from this map that the sun hours runs about 3.5 hours around Seattle and maximizes around Las Vegas at 6 hours in the wintertime. So how do we overcome that shortage of hours? So one of the ways we do that is we increase the size of our battery bank. And by increasing the size of our battery bank, say to 400 amp hours, then we can charge that at 40 amps instead of 20 amps. So we've doubled our charge current. And by doubling our charge current, then we do the math here on the left, come out to about 6 hours instead of 9 to 10 hours. We're looking at quite a bit less, but not half, because with the slope and the absorption phase here gets less and less efficient as it goes towards the right, and the time that you're saving as you increase or you double this amp hour capacity again, but has a diminishing return. So this is nearing the efficiently cost-effective limit of that at 400 amp hours for this particular setup. On the other hand, lithium only has a bulk stage. If you got a purpose-built charger for lithium, then it's going to go through the bulk. The voltage will come up to a point, and as soon as it gets there, it says, okay, I'm done, and it will go ahead and shut off the charge cycle. Lithium, on the other hand, is much more straightforward when it comes to how to calculate its recharge time. So if we got a 100 amp hour battery and we're charging it at 20 amps, and we do that for our 5 solar hours, we're going to get 100 amp hours back. So it turns out lithium is a great match for the solar hours that most of the United States has. Now, there is a little bit of inefficiency. You don't get 100% of what you put in stored. So you count off, 3% or so of that, and you'd end up at 97%. But again, lithium doesn't really care if you don't quite get it back to 100. It doesn't have some sulfation thing going in there. It actually would prefer that you didn't charge it back to 100%. So if we run the numbers here between the two banks that are sized for a 5-hour recharge, and we never did get to 5 at the 400 amp hour, but within 6 anyway, the one lithium battery is going to be roughly equal to about 4 lead acid batteries of the same amp hour rating. So the cost breaks down to, you're still going to end up paying more for the lithium, but by the time you factor in the twice the size for the charge controller and twice as many solar panels, then you've basically lost any financial advantage to going with lead. Okay, I've made up this chart to help you see the cost of the lead acid trying to hit that sun hour rating so we can recover that battery bank during a given solar day. So the pink zone covers the 4.5 to 6 hours of sun hours, and the numbers on the left represent the number of hours to recover a particular battery, and the red line down here shows that at the top, if we got a battery that we're draining to 50% depth of charge, that it will take about 9.5 hours, and as we decrease the depth of charge, then we're able to increase our current, and we're reducing the number of hours that it takes to recharge this thing. So we have to get down into about the 25% or so in order to get down to 6 hours. And if you live on the East Coast, then you only have 4.5 hours. You really need to get it down to 10% depth of charge is all you're using if all you're going to do is use the sun to recharge your batteries. Vice the lithium here with the green line, it kind of lives in that zone no matter what the depth of charge is. So it is very flexible as far as recovery time for solar. Listen to a lot of guys talk about battery charging, and one thing kept coming up is the problem of over discharging batteries, and particularly RVs, where the RV owner is not an expert in this sort of stuff, And understandably, he just uses his battery until the inverter shuts off, and then he figures that's the indication I need to recharge my battery. And he'll start his generator up and recharge his battery. And what he's doing there, we'll take this example here. We got, say, an inverter that shuts off at 10.7 volts. And if we apply a 200 watt load to that, we're drawing 20 amps out of our battery. It's very common to have a 100 amp hour battery in a RV. So if we're draining that at 20 amps, then it follows this curved line down to the 10.7 volt point on the chart, and we drop straight down, and that tells us we've discharged that battery to 13%, which is obviously way below the 50% point that we were told to stop at. I'm going to look at that abused battery and what actually kind of can happen with that. Sterling Power in Australia did some research where they basically discharged a battery till it was dead and then recharged it at 20 amps, which is just fine for the lithium. It only lost about 1% of its capability. An AGM that they were doing the same thing to, way past what the manufacturer admittedly tells you to do it, but people do that all the time apparently on these RVs, and it was down to only half its capability in 3 months. And the budget deep cycle battery, it lost half its capability within 2 weeks of cycling it once a day. Okay, so let's say we're going to build the battery backup system that we're just going to put on the shelf and maintain and not use it. So we're just dependent upon the shelf life of the battery, not the cycles that it can take. So a shelf life of the lithium, somewhere between 10 and 20 years. The lead acid, assuming we were going to store this system that could be recovered by solar within that 5 or 6 hours, you're going to end up with 4 batteries, and you're going to have to change them twice as often as the lithium battery. So you're going to end up buying 8 batteries instead of the single lithium battery. So your cost ends up being more for that size system than the lithium over a 20-year period. Okay, let's say if we build a system and we're going to use it every day. We're going to cycle it down to 90% of its charge for lithium or 50% charge for a lead acid, and with the 4 batteries of lead for every battery of lithium based on something that could recover in a solar day, no generator backup, or at least for normal routine use. So you end up having a whole lot of batteries. You got 16 lead acid batteries for every one of these lithium batteries. So the cost is more than double what it would be for the lithium. But there's one thing we haven't taken into account here is that 4 battery lead, we were only discharging it to 25% instead of 50% of depth of charge. So when you're doing that, the battery will give you about twice as many charge cycles. So instead of having to change this out every 3 years, we're only changing it out every 6 years. So we got a win for lead in this case. It's a little bit closer to the lithium, but still more. And I know what most of you are thinking, this is just way too expensive for me. So let's look at some more cost-effective solutions. We can get this 15 amp hour Bioenno battery and run it at a 30% duty cycle with a 5-watt transmitter into the repeater or something. We can do that indefinitely. So that could function as your basic power supply from day to day. Or in a pinch, if the power goes out from full charge, it would last over 9 hours. And also this 15 amp hour battery has a 30 amp max continuous, so you could use this to drive an HF rig for a period of time if you needed to in a pinch. The battery just below this, the 12 amp hour, only has a 20 amp max continuous capability, so you couldn't run an HF rig at 100 watts from that. Stepping up a notch here to a 30 amp hour battery, you could run a 100 watt HF rig indefinitely on that while it's charging at a 20% duty cycle. Or if you were just using it for your mobile VHF rig at low power, you could run if you're running a 10% duty cycle with it unplugged, it would run for 33 hours and give you plenty of capability in the emergency. Okay, well, that completes part one. The next part of this video, we're going to cover some equalization, how to parallel and series batteries, and how to do the calculations on amp hours and voltage for those, what means to balance charge, top balance charge a lithium battery, and why we need to do that, and if you can use your old lead acid battery charger on a lithium battery monitoring system, so you can figure out how much is left in my battery, whether it's lead or lithium, and hydrometers and a couple other miscellaneous things. So hope you join me on the other side.